The deepest physical hole humanity has ever managed to drill into the planet stops at exactly 12.2 kilometers. Compared to the true mathematical radius of the Earth, which stretches 6,371 kilometers down to the planetary core, that 12-kilometer bore is a microscopic scratch on the surface. Physical penetration past the upper crust becomes an engineering impossibility very quickly. The ambient temperature climbs to thousands of degrees, and the crushing lithostatic pressure turns solid steel drills into soft putty. This creates an immediate scientific problem. We are completely locked out of the deep Earth. Yet geophysicists possess highly detailed, globally accepted maps outlining exactly where the rocky mantle ends and the metallic cores begin. Every accepted fact we have regarding the deep Earth is the result of indirect geodetic deduction. We map the interior without ever digging into it. The process starts when two locked tectonic plates overcome their friction. They slip, releasing a massive, sudden burst of kinetic energy from a central point deep underground, known as the hypocenter. That kinetic energy doesn't stay localized. It radiates outward in all directions simultaneously, rippling straight through the solid rock as seismic waves. When those waves finally reach the surface miles away, they are intercepted by highly sensitive instruments called seismographs. This image shows how those resulting micro-vibrations are physically captured. An isolated stylus draws ink traces across rotating paper drums, recording the exact moment the ground shifts. By measuring the exact shape, speed, and arrival time of these specific ink traces, geophysicists can mathematically reverse engineer the density of the unseen materials the wave passed through to get to the station. This global network of seismograph stations functions as a continuous planetary-scale sonogram, mapping the deep interior through a constant stream of intercepted kinetic data. When an earthquake occurs, it generates two primary types of body waves that travel directly through the planet's interior: primary waves, or P waves, and secondary waves, or S waves. P waves are longitudinal. The energy travels in the same direction as the wave, pushing particles together in compression and pulling them apart in rarefaction. Because of this mechanical action, P waves propagate freely through all states of matter, moving straight through solids, liquids, and gases. S waves are transverse waves, creating vertical shear that displaces rock up and down in crests and troughs. This creates a critical mechanical limitation. Liquids lack structural shear strength, so an S wave cannot physically exist in a liquid medium. Upon hitting fluid, the wave instantly dissipates. The survival or death of an S wave provides geophysicists with an absolute binary test. If an S wave disappears, it proves the presence of liquid deep underground. When an earthquake triggers, it fires red S waves and blue P waves into the mantle. The S waves travel cleanly until exactly 2,900 kilometers down, where they hit a boundary and terminate. This internal termination creates a surface anomaly. Seismographs past 104 degrees record absolutely zero S waves. This massive surface blind spot is known as the S wave shadow zone. It covers 40% of the entire globe, representing a highly specific void in the data. The geometry of this shadow zone identifies a massive liquid outer core, establishing its upper boundary at exactly 2,900 kilometers deep. Isolating the blue P waves, their compressive nature survives the liquid core boundary, but the density change causes them to drastically decelerate and refract, bending sharply inward. This alters their exit trajectory, creating a smaller P wave shadow zone exactly between 104 and 150 degrees. The way these waves bend tells us exactly what this liquid layer is made of: an incredibly dense, swirling ocean of molten iron and nickel. As these electrically conductive metals swirl around the solid inner core, their motion generates a planetary-scale electrical current. This rotating liquid iron dynamo creates the Earth's magnetosphere, providing the magnetic shield that deflects lethal solar radiation away from the atmosphere. When we pull back from the core to re-examine the uppermost 400 kilometers of the planet, we find that the chemical composition of the rock and its physical mechanics begin to diverge. This diagram shows the traditional chemical model. We divide the rock by mineral type, placing a thin, chemically lighter crust directly atop a massive, chemically denser mantle. But seismic waves map a competing mechanical model. focusing strictly on structural rigidity and heat. Under this mechanical model, the outermost layer is the lithosphere. This is a rigid, brittle shell that encompasses all of the crust and the very top sliver of the solid mantle, reaching down to about 200 kilometers. Immediately below the lithosphere sits the asthenosphere, stretching down to the 400-kilometer mark. Here, the immense heat renders the rock semi-molten, ductile, and mechanically weak. Because the asthenosphere operates as a slow-flowing, highly viscous fluid, the rigid, fractured tectonic plates of the lithosphere above it literally float. They are dragged horizontally by the deep convection currents churning below. It is this specific mechanical layering, solid, brittle rock sliding over weak, flowing rock, that dictates the entire geological architecture of the surface world. When these massive, floating lithospheric plates move, they inevitably collide at their boundaries. The outcome of these collisions is dictated by a strict density disparity. Oceanic crust is composed of heavy basalts, clocking in around 3.0 grams per cubic centimeter, while continental crust is made of lighter granites, closer to 2.7. During subduction, the denser oceanic plate is forced downward beneath the lighter continental plate. As it plunges into the immense heat of the asthenosphere, the rock melts. This creates highly pressurized, buoyant magma pockets that immediately push back toward the surface. This deep mechanical destruction violently ruptures the surface crust above it, resulting in the explosive creation of volcanoes. If we map these subduction boundaries globally, they form the Pacific Ring of Fire. This specific perimeter concentrates 90% of the planet's tectonic and volcanic destruction into a single, continuous boundary. Every volcanic eruption and earthquake along this perimeter provides a localized release of immense kinetic energy. These pulses continuously power the global network of seismic waves, providing the exact data humanity requires to map an interior we will never physically reach.